Hello, in this lecture I will explain what is mathematical induction. Mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. A natural number is a positive number that is integer. All the integers that are positive are considered as natural numbers. 0 is not considered as a natural number because 0 is not considered as a positive number. Okay, so as I've already said, mathematical induction is a logical method to prove that a statement, a claim, or an equation is true for all the natural numbers. Actually, we have two steps in the process of proving that something is true according to the mathematical induction. We have step 1, that in this step we actually check the claim or the equation or the statement for n that equals to 1. We check whether the equation or the statement is true for n that equals to 1, and if it is indeed true for n that equals to 1, then we will move to the second step. The second step, in the second step, actually, we will assume that the statement is true for n, and then we will prove it for n plus 1. So the induction's hypothesis or the induction's assumption is that the statement is true for n. So in this way we will create the first expression that actually says that the statement is true for n. We assume that the expression 1 is true. This is the induction's hypothesis or induction's assumption, that the statement is true for n. Then we will rely on this thing in order to prove that the statement is also true for n plus 1. So if we can prove that the statement is true for n plus 1, then we actually proved that the statement is true for all the natural numbers. And I will explain why, or what is the logic behind the mathematical induction. You should remember that in the first step we checked the if the statement is true for 1, and we verified that the statement is true for n that equals to 1. And then we proved that if the statement is true for n, it is also true for n plus 1. That is what we already did. Okay, so according to this general proof that if the statement is true for n, that it must be true for n plus 1, we can say that the statement is true for n that equals to 1 because we have already checked that it's true for n that equals to 1, and according to our general proof it must be true for n plus 1. That is to say, it must be, and now n equals to 1, so it must be true for 1 plus 1, so it is also true for 2. Now that we know that it is true for n that equals to 2, so we will repeat the same process again. We know that it is true for n that equals to 2, and according to our general proof that if it is true for n, it must be true for n plus 1, then it is, if it is true for n that equals to 2, it must be true for n plus 1, that is 2 plus 1, so it is also true for 3. And we will repeat on the same process again. We know that it is true for 3, and for our general proof, from our general proof, it also will be true for n plus 1, that is 3 plus 1, that is 4, and so on and so on. So in this way, we proved that the statement is true for all the natural numbers, and that is exactly what we wanted to prove. We wanted to prove that the statement is true for all the natural numbers. Okay, so now I will give you two examples in order to clarify the topic. So the first example will be one plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. So actually this is our claim or statement, or you can call it whatever you want, or equation, that we have to prove it, that this equation or statement or claim is true for all the natural numbers. Or it actually says that the sum of the natural numbers until n equals to n times n plus 1 divided by 2. So we will start with the first step. That is to say, we will check this statement for n equals to 1. We will check if that statement is true for n that equals to 1. Okay? So we will check in the left side of the equation. We will get 1. It equals equals to so we check this statement for n that equals to 1, and we actually got that in the left side of the equation we have 1 because n is equals to 1, and in the right side of the equation we have n times n plus 1, and n is equals to 1, so it is 1 times 1 plus 1 divided by 2. So it is 1 times 2 divided by 2, or 2 divided by 2 equals to 1, and 1 equals to 1. So we passed the first test, or the first step. We verified that this statement is true for n that equals to 1. Now we will move to the second step. That is to say, we will assume that this statement is true for n. In this way we will get the first expression, and then we will prove it for n plus 1. We will prove that this statement is true if for n plus 1, and we rely on the proof that is true for n plus 1 on our assumption that it is true for n. Okay? So we will write down the first expression, that is the induction's hypothesis or induction's assumption that our statement is true for n. So it is 1 plus 2 plus 3 plus n equals, so n times n plus 1 divided by 2. So actually expression 1 is the induction's hypothesis that our statement is true for n. That is to say, 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. And according to the assumption that the statement is true for n, we will prove it for n plus 1. So we will write down now the expression for n plus 1. That is what we have to prove. Okay? We have to prove that expression two is true for n plus 1. Okay? We will write down expression 2. Expression 2 will be simply 1 plus 2 plus 3 plus n plus n+1, because we need to prove that our statement is true for n plus 1. So in this statement, wherever is written n, we will write n plus 1, because we need to prove that this statement is true for n plus 1. So wherever it is written n, we will write n plus 1. So here it will be n plus 1 times n plus 1 plus 1. Okay? So we need to prove that expression 2 for n plus 1 is true, and expression 1 is for n plus 1. So it is 1 plus 2 plus 3 plus n plus 1, because this expression is for n plus 1 equals 2. Wherever it is written n, we will write n plus 1. So here it is n, here it is n, so we will write n plus 1, and we open brackets. Here again it is written n, so we will write n plus 1, n plus 1 plus 1, so we add 1, and we'll close the brackets, all divided by 2. So we assume that expression 1 is true, and we will rely on this in order to prove that expression 2 for n plus 1 is also true. Okay, so now in order to prove expression 2, we should look on this expression. This expression actually equals the expression that is on the green the expression in the green color. Okay, so 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2, and this is according to our assumption, and we assume that our assumption is true, so we can substitute this expression by n times n plus 1 divided by 2. Okay, so we will do it now. So we actually substituted this expression by n times n plus 1 divided by 2, because according to our assumption the statement is true for n, and the statement for n says that 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2, so we can substitute those two expressions because they are equal to each other according to our assumption, and then we have here n plus 1, so we will leave it as it is, and we have to prove that all equals to n plus 1 times n plus 1 plus 1, all divided by 2. Okay, so we know that n plus 1 is n plus 2, so we will write it down. So here n plus 1 is n plus 2. So we have here n plus 1 times n plus 2 divided by 2 equals to n plus 1 divided by 2 plus n plus 1. So now we can divide both sides of the equation by n plus 1, because n plus 1 can never be 0, because n is a natural number, so we can divide both sides of the equation by n plus 1. Okay? So after we divide both sides of the equation by n plus 1, we got here what is left, that n divided by 2, and n plus 1 divided by n plus 1 is 1. And here we divided this expression by n plus 1, so what is left is n plus 2 divided by 2. Now we can separate n plus 2 to two parts, and we will get that n divided by 2 plus 1 equals to n divided by 2 plus 2 divided by 2, because we separated n plus 2 to two parts. And here 2 divided by 2 is 1, so we'll get the final result that n divided by 2 plus 1 equals to n divided by 2 plus 1. So we got that n divided by 2 plus 1 equals to n divided by 2 plus 1. So actually we succeeded to prove that the second expression for n plus 1 is true when we assume that the expression for n is true. And in this way, we actually succeeded to prove that our statement is true for all the natural numbers. Okay, our statement that 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2. Why? Because as I have already explained to you, we have already checked that the statement is true for n equals to 1. And we now proved that if it is true for n, it must be true for n plus 1. So we showed here that it is true for 1. And from our general proof that if it is true for n, it is also true for n plus 1, we actually can say that n equals to, for n equals to 1, it is true, because we checked it that is true, so it must be true for n plus 1, that is 1 plus 1, so it is also true for 2, and we will continue with the same process. We know that it's true for 2, and from our general proof that if it is true for n, it is true for n plus 1, then if it is true for 2, it must be true for 3. If it is true for 3, it must be true for 4. If it is true for 4, it must be true for 5, and so on and so on. So in this way, we showed that our statement 1 plus 2 plus 3 plus n equals to n times n plus 1 divided by 2 is true for all natural numbers. Okay, now I will give you the second example. that we will prove it by mathematical induction. That is to say, we will prove that the statement is true for all the natural numbers. One to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n square times n plus 1 square, all divided by 4. So this is the second example. We have to prove for all natural numbers that 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 square divided by 4. Okay, so we will start with the first step, and we will prove that this statement is true for n that equals to 1. Okay, so we'll check that indeed the statement is true for n that equals to 1. If n equals to 1, we have in the left side of the equation 1 to the power of 3 equals to 2. So we have in the left side of the equation 1 to the power of 3, that is equals to 1, yes, and in the right side of the equation we have n squared and n equals to 1, so it is 1 squared, and we open the bracket, we have in the brackets n plus 1 square, so it is n equals to 1, so it is 1 plus 1 square, all divided by 4. 1 square is 1, and 1 plus 1 is 2, so we have 2 square, 1 times 2 square, all divided by 4. 2 square is 4, so 1 times 4 divided by 4. 1 times 4 is 4, we have 4 divided by 4, equals to 1. So finally we have 1 equals to 1. So we actually proved that the statement is true for n that equals to 1. Now we will move to the second step, and we will assume that the statement is true for n, and we will prove it for n plus 1. So we will have the hypothesis that says that our statement is true for n. The first expression is expression that says that our statement is true for n. So the induction hypothesis says that our statement is true for n, that is to say 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared, all divided by 4. And we will rely on this assumption in order to prove that our statement is true for n plus 1, okay? So the second expression will be an expression for n plus 1, and we must prove that our statement is true for n plus 1. That is the thing that we need to prove. And we will rely to prove the second statement on our first statement, that we assume that it is true. Okay. So we have to prove that our statement is true for n plus 1. And the second expression is our statement for n plus 1. That is the equation that we have to prove. And this statement, the second expression, n is for n plus 1 because it is 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 plus n plus 1 to the power of 3, because we have to prove the statement for n plus 1 equals, here, wherever it is written n, we will write n plus 1 here, because we must prove the statement for n plus 1. So here it is written n squared, so we will write n plus 1 squared. Here it is written n, so we will write n plus 1. It is n plus 1, so it will be n plus 1 plus 1 squared, all divided by 4. So we must prove that the second expression is true. And again, we will make the same process. We will look on this expression, and according to the expression actually that is on the green color, we know according to our the hypothesis in the induction hypothesis that this expression equals to n squared times n plus 1 squared divided by this expression is equals to n squared times n plus 1 squared all divided by 2. Okay, so we can substitute this expression by this expression because they are equal to each other according to our assumption. Okay, so we will do it now. So here we substituted this expression by this expression because according to our assumption they are equal to each other. That is the induction hypothesis. So we substituted this expression by this expression because they are equal to each other according to our assumption. And then here is written n plus 1 to the power of 3, so we left it as it is. All equals to n plus 1 square and here n plus 1 is n plus 2. So we wrote here n plus 2 all square divided by 4. Okay, so we must prove that the second expression, that is the second expression, is true. Okay, so now we actually can divide the two sides of the equation by n plus 1 squared because we have in both sides n plus 1 squared. So we will do it now. So after we divided this expression by n plus 1 squared, we got n plus 1 divided by 4 and n plus 1 to the power of 3 divided by n plus 1 squared. What we left is n plus 1 all equals, we divide this expression by n plus 1 squared and we left, what is left is n plus 2 squared divided by 4. Okay, so now we will open the brackets in the right side of the equation, or better thing to do is to multiply both sides of the equation by 4. Okay? So after we multiplied both sides of the equation by 4, we got n squared divided by 4 times 4 is n squared, and n plus 1 multiplied by 4 is 4n plus 1, and n plus 2 squared divided by 4 multiplied by 4 is n plus 2 squared. Now we can open the brackets. And the final result is n squared plus n squared plus 4n plus 4 equals to n squared plus 4n plus 4, because n plus 2 squared, it is like a plus b squared, that equals to a squared plus b squared plus 2ab. So it is a squared, it is n squared plus b squared is 4 plus 2ab is 2 times 2n is 4n. Okay, so we actually proved that our expression is true for n plus 1. Okay, our expression 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus n to the power of 3 equals to n squared times n plus 1 squared divided by 4. This expression is true for n plus 1, and therefore it is true for all the natural numbers, because we assumed that it is true for n, and from this assumption we have proved that it's also true for n plus 1. And in this way we proved that it is true for all natural numbers, because we actually verified that it's true for 1, n equals to 1. And from our general proof that if it is true for n, it is also true for n plus 1, we can say that if it is true for n equals to 1, it's also true for n equals to n plus 1, that is n equals to 1 plus 1. So it is true for 2. And we will repeat this process. If it is true for 2, it is true for 3. If it is true for 3, it is true for 4. If it is true for 4, it is true for 5, and so on and so on. And in this way, we actually proved that this expression is true for all natural numbers. Okay? Thank you very much.